I'm Erica Carlson, a theoretical physicist here at the Purdue Quantum Science and Engineering Institute. Welcome to Quantum Interviews, where we have interesting conversations with people working on all things quantum. I have with me here my colleague Vladimir Dobrosavljevic, who can correct my pronunciation if needed. He's a professor of physics at Florida State University and at the National High Magnetic Field Lab in Tallahassee. Welcome.
Thank you, Erica. This is wonderful to be here.
Glad you could join us. So one of the things we like to ask people is, what got you interested in science, interested enough to make a career of it?
Well, you know, I didn't plan to do a career in science, but then my grandmother bought me the Berkeley Physics course book. And when I opened this book, I discovered that actually physics is interesting. I was genuinely surprised. Yeah. I thought it would be boring, but then since that moment, I just couldn't stop. I was really impressed.
You thought it would be boring, so like, what made you think it would be boring? Because you're not boring, I'm not boring. Why do people have this impression?
Because I come from a family of physicists, and I, like all teenagers, I thought that whatever my parents do, it suddenly has to be something stupid. So I didn't think I was nerdy stuff, but turns out it's a lot of fun, and there's always something surprising and exciting, and after all these years, I love it.
Awesome. So the Berkeley physics course, though, that would be something that most people don't get their hands on in a way that they can really understand until they're pretty old, as in the high school, college really. And this is a college set of textbooks. So was there some other thing as well, or were you reading this when you were 5 years old? I mean,
not, but actually, there is something interesting. I was in the corridor. I was coming here, and there was a display on Einstein, and it says that what got him interested as a teenager, maybe, when he was learning Euclidean geometry. I actually had the same experience, not that I'm as smart as Einstein, but my hairstyle is better. I remember in high school, I really didn't like school. I hated all the teachers. Now I'm one. Can you believe it? But when we learned Euclidean geometry, I was really impressed because it was very logical, and that's something you can really believe, as opposed to everyday life where there is so much controversy about stuff, lies, about this and that, but in Euclidean geometry, you can be certain that something is right and you can prove it. And I said, wow, this is really amazing. I tried to teach my grandmother, who was a German professor. I said, I have to teach you these theorems. And I said, well, Vlad, I'll make you a cake, chocolate cake. So I said, okay. But I was really impressed. That actually is probably the first time I really got impressed by science. And I think the reason is that it's really something you can believe, which is incredible.
Very nice. I think that's one of the things that got me inspired about science too, is this element of there being truth that you can sink your teeth into and you can verify and stuff like that. So why do you think people are so interested in all things quantum right now? And in particular, you and I both work in the field of quantum materials. Why are people interested in quantum materials right now?
Well, there has been a lot of progress recently, and when I was a kid, we had this first little calculator, and I was like, wow, could never imagine that one day even with an iPhone, you could do all those crazy things. So there has been a lot of progress, and I don't need to explain that today we have the ChatGPT and things like this. It's just the progress has been so amazing that if I often say to my students, if someone showed you an airplane and said this can fly, this huge heavy object can fly, and if you didn't know it was an airplane, you said there is no way. And today things like this that are unbelievable are so many. We have this huge revolution in AI. We can talk to a computer. There are lots of things you can do which are truly surprising, and it's amazing that we actually have an understanding how this works. And a lot of these things have to do with something that we could never understand based on all the ideas of classical mechanics. I think we really need quantum ideas. And in the context of quantum materials, I always say to my students, that the electrons, because they're like alligators, they don't like to share the territory with each other, right? This is what alligators do.
You're the only physicist I've ever heard make that analogy.
No, it's because I live in Florida, and in Florida, the alligators, people are afraid of them, but they actually have a nest, and they don't let anyone nearby. And so if you get there, they'll kill you, but if you're not come near, they won't even look at you. And the same with the electrons. They're on quantum states. They protect it with their dear life. And this is the reason why the electron had to populate these states. And so at the end of the day, even in their lowest energy state, the electrons are forced to move with incredible velocity. Mm-hmm. And I just looked up, I was preparing a talk recently, the typical velocity of electron is 1,500 kilometers per second, which is about 1,000 miles per second. Each second you travel 1,000 miles. That's super fast. It's faster than a jet airline. And when
Sort
you
of
think
scarier than an alligator at that point.
maybe that's, well, I guess, but the point is that if you try to describe how something moves,
Yeah.
if you're trying to go up the hill, well, it's good to run fast and then you go a little bit higher up, right? So running fast will help you get somewhere. Well, this is why the electrons, they really go somewhere, they go places because they are running so fast. And without quantum mechanics, we could never understand why are they going so fast and what do we have to do to control their motion. So you think if someone goes that fast, there is no way we can control them. There is nothing we can do to them. But no, we actually can. We have learned tricks in quantum mechanics, how we can make them move and make them stop. And this is how we can build all the quantum computers and everything. Because we understand this motion and it's something really different than the way that a football moves or an airplane or a train. So this is where quantum mechanics enters, and it's something completely different, and it completely, people ask me, what do you do? I say, I do quantum physics. Really? There's no way. I say, yeah, this is all I do all day long, and this is not such a big deal, but without it, people say that we couldn't even understand why gold is yellow.
There we go. So you do a lot of great research. That's why we're here. That's why we're here together. We invited you to come, to the physics and talk about your research.
I want you to share. You have to share this video with my referees, because if you say that it's great, maybe they'll let me publish my paper.
Obviously, we will definitely copy this to all your referees. But so you do a lot of great research. Of all the research you've got going on right now, what's the thing you're most excited about that you'd like to tell us about today?
Well, all my work has to do with understanding how the electrons move and how they stop, and are there conductors or insulators, and there are many facets of this research. But one thing that I really, enjoyed is the fact that this physics applies to conductors, to insulators, to devices, to electronics and things in the lab. But we discovered that these ideas are actually relevant, something I discovered very recently, because our own son is actually also a scientist, but he studies the properties of materials deep under our feet, near the Earth's core. And turns out that the same ideas of quantum criticality, it's called, which have been discovered to understand the properties of materials like little transistors in your computer, well, the same ideas actually apply to planet Earth, and they explain how the heat from the iron core is able to surge up and form these heat plumes when they hit the Earth's crust. This creates volcanism in Hawaii. So this is incredible. You'd never think that so deep inside below our feet, something happens that is very similar to what happens in the laboratory, and we just didn't know about it. So I found that very exciting, that you see that often in science that the same ideas that are discovered in one field, they can actually explain what happens in many different fields, and there is a common theme. It's an amazing thing to discover that simple ideas can be applicable to so many different examples in everyday life.
Very nice, including volcanoes in Hawaii. So you just made a connection between volcanoes in Hawaii and quantum criticality. Can you kind of give us a layperson's explanation, a quick idea of quantum criticality?
Well, so quantum criticality is something where you completely change your behavior in the lowest possible energy state. And that means that if you are faced with a decision, you have to go decide, I'm going to go this way or that way. It may take you a while to decide which way to go. But before you take the time, in the intermediate state, you are kind of undecided, and then you're doing something that's completely different. It's like in this country, we have the Republican, the Democratic Party, and there are some undecided voters. Now, it's really true that those who are undecided, they could actually be completely different in every way than belonging to either group. So this quantum criticality is something that is, in fact, a different state of matter than the phases that we are familiar with, and people usually assume that either we belong in one camp or the other, but it turns out that a large number of examples in everyday life are governed by quantum laws, but the behavior that you find is actually quite different than in familiar phases or in familiar situations, and we have to discover how it works. Another reason why this is actually important, and this is generally true, when you raise the temperature, this intermediate region broadens. So we can find a broad region of parameters where some completely new phenomenon is found, and in particular in planet Earth, this means that metals, they have a very high conductivity. They conduct, electrons move like crazy. In insulators, they don't. And in these intermediate regions, there is some intermediate level of conduction, which has been a big puzzle to the geophysicists or the seismologists for a long time. How can that happen? Is it a metal or is it not a metal? They only thought of these two options. But then it turns out that there is an intermediate way to behave, and in political life, maybe there'll be more parties in the future. Who knows? In Europe there are more parties, but it could be something different, and maybe sometimes different is better.
Nice. Okay, so the idea was that there was this sort of intermediate conduction regime where the electrons really are exhibiting quantum phenomena at a large enough scale to affect the geophysics. That is awesome. That's really cool. All right, so we're out of time, but thank you so much for talking to us today on Quantum Interviews. Appreciate it.
It's a real pleasure.